As you will find out momentarily, the search for dark matter comes in many different forms and technologies. We're fortunate to have Rick because he's one of the very few people who's actually worked on a number of different ones of them. That I don't know, but he's still on one experiment, so he presumably still has some bias. But he knows everything that you would ever want to know about all these different searches, and today he's going to tell us how we're doing. So,
Neil, thank you very much. So, you know, the universe has been something that we've gone through various stages of seemingly completely understanding, and then not understanding so well. And of course, I think it will be fair to say that the last 35 years, really the sort of post-Apollo bonus we've all received in terms of funding has allowed us to progress enormously, and it will be, I think, looking back, it will be viewed as a sort of renaissance period in terms of our understanding of how much our understanding of cosmology and astrophysics has advanced. Of course, one says that with the appropriate apology, which is we still don't know what 95% of the universe is made of, right? Now, I thought about obviously taking you through all of this various evidence for and thing, and then I thought I'd just spoil it, and since everybody is getting more comfortable with this idea, that this, say, is the composition of the universe that we understand today. And one of the interesting things is that we are a subdominant part of it. The conventional material, the baryons, the electrons, neutrons, sorry, it's, baryons meaning protons and neutrons, the electrons that we're made of, are just this small sector here. And in fact, the bit that you're really comfortable with, the stars, the bit that's luminous or luminous in a very sort of conventional optical photon sense, you know, the stars is less than 0.5% of the total composition. You know, the majority of the universe, it turns out, is this combination of dark matter and dark energy. Now, we're also at a point where, and these were the numbers from a few years ago, we're also these days at a point where we actually argue, if you like, about the second significant figure on these numbers. Our experimentation, our results are so good that the error bars now are just at a few percent. And I put this up partly to point out that for the first time in a while, as I'll show you in a moment, dark matter was sort of going down and down and down, but this dark matter component actually in the latest you know, set of results as influenced by you know, by Planck and a number of you know, surveys of structure in our universe. We're at about 27% dark matter component, 68% dark energy. Now let's.
This is in the past year or two?
Yes, yeah, in the last year and a half, I think, was when, you know, the revision to the numbers using Planck data. So that's the conclusion. How did we get there? I mean, just in terms of the last 30 years, which is the sort of period I've spanned this work. In the 90s, if you like, it was a known that omega, which is this dimensionless quantity which relates, one way of thinking about it is it just tells you about the how any given component of the universe compares to the amount of that thing that there would have to be in order to generate a flat geometry, in the, you know, in the sense that parallel lines within three-dimensional space stay parallel. So it was known through CMB observations and, if you like, through, well, ultimately through CMB observations, but also it was a sort of general prejudice, you know, built on inflation possibly, but it seemed natural for the total energy density in the universe to indeed be 1, but we also kind of knew that it was a matter dominated, that actually 100% of the universe was some form of matter. Now, of course, it turns out that was not the complete story. The reality, as I've just shown you with the conclusion, was that it was found CMB did indeed confirm, and has done so repeatedly, to show that omega total, the critical density, is indeed 1 in our universe, but that matter is only of the order of 30% of that number, and that the other 70% or 67% is in the form of the, you know, this dark energy, and that the way you have to account for this is since luminous matter, conventional matter, luminous matter, the stars are much less than 1%, that you have three dark problems. You have the conventional baryonic material, dark matter, which is, if you can picture that graph or pie chart I just had up, is mainly in the form of the sort of intergalactic baryonic material. But then you have what is referred to as a non-baryonic, i.e. non-conventional material, dark matter problem. That's the one I'm working on, which is known. And then you've got dark energy, which, as fascinating a problem as it is, and the way in which it has properties which are very different from that of the dark matter, is from a point of view of actually identifying it, is clearly going to be quite the challenge. So let's just focus on dark matter. And as I said, there's been a hell of a revolution over the last 30 years, just because our ability to really do what's often referred to as precision cosmology has improved enormously. We've got very good at being able to truly characterize systematic effects in our observation, while we've had very much more comprehensive observation programs that really have led us to this really quite precise understanding of the composition of the universe. And then we find that this solution to the dark matter problem mates very nicely with a sort of fundamental physics, particle physics problem, which is that of what happens next, what happens above the standard model. And the problem, or the way in which I've been approaching dark matter, is certainly to try to unify the two, in the sense that we're designing experiments designed very specifically to look for weakly interacting massive particles, which are a specific solution of that would come out of particle physics, but would also have exactly the right properties in order to provide cosmology with its solution. And the way we're focusing in on that is what's called direct detection, which I'll take you through a little bit of, but it's essentially just using detectors to look for the occasional interaction of dark matter particles in them, direct detection. But there's also what we call indirect detection, which is we try to look for the signatures associated with this dark matter annihilating. The dark matter abundance was determined by annihilation in the early universe. And it's this thing that's often referred to as the WIMP miracle that really got us excited about particle physics solutions for the missing mass of the universe, the dark matter, because annihilation cross-sections of the order of the kind of physics we're currently interested in, the weak scale if you like, give you a natural abundance for these particles, which would indeed provide this 30% of the missing mass or density. So what we can do, therefore, being fairly confident that such annihilation is part of the package, you can then just go looking for this signature. For instance, there's a lot of excitement at the moment about potential signals in Fermi satellite of gamma rays that may be sourced by dark matter particles from the galactic center. The only issue there is, of course, the galactic center is a horribly busy place, our own galactic center, and therefore there's no shortage of other signals which may or may not be confusing that signal. But then, of course, the other way in which we're searching for WIMPs, these weakly interacting mass particles, is very directly using the Large Hadron Collider, whose energy has just been upgraded, the luminosity has been upgraded. So the next 4 years, although I think we can all describe it as a bit of a disappointment that, the last 4 years that we didn't see evidence of new physics, of new particle physics in the LHC. That was just that was the sort of first low energy, if you like, run. Now we're going to try again at its sort of design energy and very close to its design luminosity, and we will be looking to create new physics, new particle physics, possibly even dark matter particles directly in the LHC. So these are the ways that we're choosing, if you like, to try to zone in on this thing that is the dominant mass in our Milky Way. The halo of dark matter particles are such that they were the thing that formed our galaxy, and if you hold your hand up, the flux, hundreds of millions, billions per second through your hand, just by virtue of a number density which corresponds very approximately to about 1 or 2, or a few in a volume like this, and they're moving with a velocity that's characteristic of the gravitational sort of or the kinetic energy of particles within our Milky Way, which is about 1,000th the speed of light. So they're a non-relativistic particle distribution, and in your vanilla model, they're essentially just a Maxwell-Boltzmann gas. They're just moving in random directions. So we're attempting to do science with particles that have, if you go, I won't do the calculation, I did it for class a bit earlier, but I'm going to state it, that the energy is, the characteristic energy is, if you figure out 1,000th the speed of light for weakly interacting massive particles with masses of the order of a GeV, that's the mass of a proton, to maybe 1,000 times the mass of a proton, or 5,000 times the mass of a proton, the kinetic energies associated with those particles moving at 1,000th the speed of light is of the order of a few keV to tens of keV. So that has always been the challenge. While we know these WIMPs are traveling with fluxes which are impressively high, the amount of energy that they're willing to deposit is very small. And then also it turns out that the coupling, the way in which these WIMPs may be coupling to ordinary matter, is the source of great uncertainty, because you need to know what the propagator is, what the particle is that couples the WIMPs to the nuclei. And right now we have many models that predict many different propagators, but we don't know what the strength of that interaction is. So as I'll show you, we're having to explore the physics over a parameter space that's at least 9 orders of magnitude variation in that coupling strength.
Is zero ruled out?
No, it's not. No, you have to. You could do it trivially by, if you want to confine yourself to supersymmetry, you use a gravitino as a WIMP, as a dark matter particle, and that has no useful coupling to. You could also get in a situation where the coupling particles, say your main source of coupling is through light and heavy Higgs, and the signs of those two terms in some scenarios exactly, or very close to cancelling one another out, and you can drive the cross section to a value that's too low to be useful. So you do not describe every. You're not, through just direct detection alone, you will not explore every possible model of WIMP. There are plenty that think. I think the way you put it is, of course, if you do get lucky in one of the channels, if, say, we make it at the LHC, or say, if we make it at the LHC, then the fact that you can't see it in a direct detection experiment starts telling you about, the coupling to the nuclear thing, or tells you something about, WIMP abundance or WIMP lifetime, because, of course, we get no real direct lifetime measurement of a WIMP as long as it's long enough to get out of your particle. If you can't see it, anyway, sorry, I shouldn't go down that. If we see it through annihilation and we don't see it through direct detection, then again, and depending on how it's annihilating, you're learning something about the particle. But it is true to say that not seeing it in any of the things, that is less satisfying. You would like to, to actually start learning something from non-observation, we really would like to have pinned it down somewhere. And although we know it exists in the sense that there has to be some solution to the dark matter, that might be considerably broader than just a WIMP. Again, there are things. So, what I'm going to try to discuss in this colloquium is what does it take to find WIMPs directly. I think, and as you'll see, we're leading to all sorts of entertaining physics. But then, of course, you can ask the question: have we discovered WIMPs? At this point, I say that because some of you who follow a bit more interestingly, may know that we have had a number of, and really even right now, situations where people are claiming discovery with various experimental results, and I want to sort of tell you a bit about that. Then you can ask from a technological point of view, if you like, either we've discovered them already and we're just trying to verify them, or, as I think, frankly, more likely, we've really got to go and, if you like, rediscover them, because certainly with direct detection experiments, I don't think we have discovered them, even though we do have some fairly strong claims about that. So have we got what it takes to rediscover them? And of course, this may happen first in the accelerators. It just depends on our dollar to sort of energy ratio. It may be that we have already detected them indirectly. And then when it comes to direct detection, in order to be competitive, in order to be with any chance of actually nailing them, seeing them, the interaction rate, and again, if I use my cup again as a sort of canonical demonstration, if we say this is the order of a kilogram, if it was germanium, this is a kilo, or xenon, if this was full of liquid xenon, then in a detector of this scale, you have to, in order to even match our best sensitivities right now, you have to run for a century. It's one interaction per century in a kilogram. Now, of course, we're not that patient, so what we've done is we've actually got up to tonne scale already, which means we've brought that interaction rate from a century down below a year. But right now, in order to build competitive experiments and be operating experiments, you want to be getting into the sort of tonne per century level. Of course, again, we're not that bloody patient, so it means you build 100 tonnes and watch it for a year. So that's sort of where this game is at in terms of direct detection at this point. Now, where's it being played? Well, all over the map, as they say proverbially. This is a list of for the most part, all the active experiments that are going on at the moment. The one I'm involved in is this one here, the LUX Experiment. But as you can see, we have experiments at various sites all over the world. To be fair, some of them are credible. A number of those experiments are not really in a position to say anything new. One sometimes wonders why they're doing it at all, but there are many, at least half of these experiments I think are up for a credible discovery, in that they are capable of exploring new parameter space. Now, myself, I've actually been looking for dark matter for 26 years, which is not quite the full extent, but bloody close to the full extent of our quest for this for these particles. My first sort of serious underground experiment was actually, it was CDMS. Technically, it was CDMS-1. We were only about 30 feet underground for CDMS-1. CDMS-2 we took to Sudan, which is about half a mile underground. We'll talk about why underground in a moment. This was up in the mine in Minnesota, northern Minnesota. I then moved to an experiment, Xenon 10, which we did in Gran Sasso. As you can see, if you go do physics Italian style, you need to change your outfit to blend in. This is how you do physics in Italy. And then latterly, back to the more salt of the earth kind of behavior at the Homestake mine in South Dakota, and of course, again, necessary wardrobe change. So, South Dakota, for those of you who have forgotten, or maybe never knew where it is on the map, I hope most of you do, of course it's here. And we're in the Black Hills, gorgeous here. The lead itself, this is an open cast or open pit mine for gold. Most of the mining activity in lead took place, it started by, in the 1870s when there was an enormous gold rush in the hills, Black Hills of South Dakota, and they chased it over a mile and a half down. We have latterly turned that into a laboratory, the Sanford laboratory, and we're operating at about a mile underground, and as well as the LUX experiment. There are a whole series of other ones, but I don't have time to mention those. For those of you not aware where Rhode Island is, it's somewhere there. No, we're so Brown University. That's where I'm from. So, history lesson in terms of direct detection. 3 years ago, 2.5 years ago, we had our silver Jubilee. So what's that, 27, 28 years old now. This was a first paper. The work had started before then, but this is the first paper on a result for a direct detection. And it was actually using a germanium detector that was designed to do double beta decay, but that was not repurposed. It was still being run as a double beta decay experiment, but it was also, they decided to say, look, we'll look at low energies. We'll try to look for these KeV, these particles which may weigh GeV, but because they're moving at thousandth the speed of light, they have KeV kinetic energies, and they come in and they're going to recoil from our nucleus, in this case germanium nucleus, and they're going to deposit energies of a few keV or 10 keV, and we're going to see whether we can see any evidence for that in our spectrum. So, and fun enough, this experiment was done about 40 feet from where we're doing the LUX experiment today. It was actually in the Homestake mine. At that time, Homestake was a fully operational gold mine. So the data looks something like this. This was after a couple of months in a detector that's ordered 0.8 kilograms. This is what the spectrum looks like, and there are a few things I should sort of clue you in on. One is that this dotted line here corresponds to a sort of standard unit in backgrounds, which will be relevant. I'll talk about it in a thing. It's the count per KV, so per bin width, per 1 KV, per kilogram per day. So one of these guys, kilogram, per day, because we're moderately patient. So that was the state of art, in the mid-80s. And as you can see, the background up here, it's a 20, 30, 40 keV, was of the order of this 1 keV. At lower energies, it turns out that cosmogenic activation and a modest amount of contamination is actually causing this thing to rise. And we have to ask ourselves a question, what would a dark matter signal look like? Well, on one level, it's quite interesting because, hey, maybe we have discovered dark matter here. The trouble is, because of the way this detector works, all backgrounds could potentially be dark matter. There's no way of differentiating them. So please. Yeah. So the blue, sorry, that's what I was about to say. So the blue line is what a dark matter signal would look like. Why does it look like that? Oh, it's a logarithmic scale, so this is an exponentially falling curve. Why does it look like that? Because when you integrate the Maxwell-Boltzmann velocity distribution of the dark matter particles in the Milky Way, and then you consider that, and if you just assume S-wave scattering, just simple billiard ball scattering, when you integrate over all impact parameters, so all possible scattering angles, it turns out that you get to leading order, and this is good over 2 orders of magnitude of recoil energy at least. Within a couple of percent, it just looks like an exponential. It didn't have to be that way, but in a sense, if you consider the way the integrals work and the exponentials floating around, it's not. And this characteristic energy is of the order of sort of 10, 15, 20 keV. It does rather depend on the mass of the WIMP. Now, there is a slight subtlety in that this is keV in equivalent, what's known as electron equivalent units. It's for an electromagnetic interaction. Technically, what we're talking about here is a nuclear recoil, and the way different detectors manifest energy for nuclear recoils as opposed to electron recoils it can be quite different. So this is actually squeezed more against the left axis than you might naturally naively calculate. But nonetheless, this would be, if in all of the correct units for this experiment, if WIMPs were interacting at a cross-section which gave you of the order of 100 events per kilogram per day in germanium, then the spectrum would have looked like this. So you can see, you can just look at this spectrum and say, well, it couldn't be 200 events per kilogram per day because that would be above, that statistically would have given you signal that was above what we're seeing here. So this is about the limit that you placed, and that's indeed what happened. You were placed a sort of upper limit on the interaction strength between, since you're pretty confident about the number density of WIMPs, or certainly to order of the mass. So another way of thinking about it is if you do need to know the mass, and since we don't know that, we have to consider that a free parameter, so that just changes the slope here. So you end up ruling out a whole series of models based on different masses and different cross sections, and I'll show you what that looks like in a moment. At the same time as that work was going on, this was what I was doing in a lab, which is actually a superconducting piece of niobium. That dimension there is only about 15 or just over 10, 12 millimeters. It's about 12 grams. That was considered to be quite an exciting detector because although it wouldn't have seen hundreds of events per day, it would have seen 1 or 2 events per day, and that was enough because we could control backgrounds to that level to look for dark matter. It was also able to do this at very low energies. It was very sensitive. It had a threshold that was well below a keV, to about 250 eV. I put this up because today we are doing the same thing, and in fact we're doing a bit better than this. We've got clear demonstration of detection of events that are at the 140 eV level, and we're doing that in 1/3 of a tonne. So 1/3 of a tonne performing in terms of sensitivity every bit as well as what we were doing 25 years ago. With, in this case, superconducting niobium, which was a bit of a pipe dream, because obviously it turns out, anyway, I'll talk about that another time. So let's show this a different way as a history plot of direct detection. So again, here we are back in '85 with the first result, the Homestake paper, and we just go through sort of order, 25 years, and this is the cross-section in physics terms of what it means to be the coupling between a dark matter particle and a nucleus, and you're doing it in assuming the most vanilla style model you have. And the cross sections we're testing initially up here, for reference, this corresponds to order 1 event per kilogram per day, so we're at the tens to hundreds of events per day up here, and these are the double beta decay experiments, and they ended up with a sensitivity that, even though it spans nearly 8-10 years, actually, these are double beta here as well, so getting on for sort of 12, 13 years. Those experiments were not optimized to do anything other than really double beta, and it turned out, it became very clear that minimizing or reducing your low energy backgrounds is very difficult. So instead, and many areas of physics research are like this, whether you consider accelerator work or neutrino work or what have you, you really need a new technology to come in to help. And the new technology that came in was we moved from germanium, if you like, to sodium iodide. Why sodium iodide? Because sodium iodide could differentiate between a nuclear recoil, which is what we expect a dark matter particle to do, a WIMP certainly, and a conventional electron recoil background. Now that discrimination, that difference was not completely cut and dried. It was statistical, but that additional statistical leverage did allow one to improve the sensitivity. What it also did, in fact, is in 1998, I remember this very well, allowed discovery. In 1998, Dharma basically came up and said, and we'll talk about this at the end of the lecture, actually claimed, and still does today, now as the Libra experiment, claims discovery of dark matter WIMPs. At that time in 100 kilos. So the thing they had over everybody was they were 100 kilos of mass. All this other stuff was kilo scale. But they had gone ahead and discovered dark matter. What subsequently happens is that these new cryogenic detectors, these guys that run at sort of 10 millikelvin, and are very good at discriminating nuclear recoils from electron recoils using phonons and ionization, they accelerated the pace at which we were able, over time, to improve sensitivity, rarer and rarer, so you're getting larger and larger detectors looking for a smaller and smaller rate of interaction. And then latterly what's happened is in purple is a new generation of noble liquid-based experiments where we really, I think, have embraced the sort of type of techniques that did us so well in neutrino physics in terms of scintillator phototubes. We've been able to push, while maintaining these incredibly low energy thresholds, we've managed to push the masses now up to of the order of a tonne scale, and will, because of the very natural way in which this technology scales, we're going to push it into thing. And what that's doing is driving you down in cross-section here in the physics, and the reason the cross-section can span, as I'll show you a bit later, so many orders of magnitude is because, in particle physics you often where you have essentially a 1 over mass to the 4th. If your propagator, your gauge particle is very massive, then unfortunately the cross-section goes like 1 over the mass to the 4th. And so any uncertainties in that nature of that and the mass of that particle really do map in very rapidly to a rapid change in cross-section. So that's where we are, and let me put it another way. You can think of what we did here in terms of running, if we run this new LUX detector as we did last year, and we are now, how much does the sensitivity that we see on this graph correspond to searching for dark matter particles with LUX? These original experiments, in the first 2 minutes of watching the new LUX experiment, instead of tonne switching on, we had reached this sensitivity. And then, of course, you just go across this and, the spanning 10 years, say, that was completely covered in 10 minutes of running the detector. And then as we go further on, by the time we'd run LUX for 8 days, or in fact, there's 28 days, we had matched the best that there was at that time in terms of sensitivity. This experiment here was the last one I worked on, the Xenon 10 experiment, which we sailed past in less than 2 days. At 28 days, we'd gone past the other one, and we stopped after about 3 months, but we're now in order, and we reported a result because we were very excited about it, and I'll show you a bit about that. But we've now gone on to, we're going to run it for a year. And this will put us at this sort of sensitivity level down here, and we'll talk about that in particle physics terms. So let me now go on to talk about some of these dark matter experiments and the way in which you design them, and the sort of results that we've been getting. So I think let's just initially focus on the best, if you like, the platonic ideal for a dark matter detector, which you could say is a detector that simply, lets out a ping every time it sees a dark matter particle, right? I mean, that would be ideal, in terms of certainly getting evidence for there being dark matter. Of course, nobody's going to believe a result from such a thing. Now, we have in fact got a detector that's bloody close to that. Let me tell you about bubble chambers. Bubble chambers came back into fashion, having done stalwart work, in particle physics through 60s, I guess into the 70s, but they were reimagined to look for dark matter. And why? Because of, very nice piece of, condensed matter physics, if you like, that comes out, which is, look, you can take a material and, we can mess around, we can just hold it at a given pressure, say, vary its temperature, and I think everybody understands, it can go from freezing, it melts, it boils, right? But of course, what you can do, if you're very careful, is you can take, and I hope everybody's done this either with, anyway, I hope you have all done this. You can take it past its boiling temperature so that it should have boiled, but because you put it in a very smooth container, it had nowhere to nucleate. And of course, the boiling process, there's nothing really magical about it. It's just when the vapor pressure equals atmospheric pressure. But you still, to let it get going, you need to sort of nucleate those, allow those bubbles to form. So if you work hard to make a container which is very smooth, you can hold things at temperatures above their boiling point, as a superheated liquid. And the nucleation site can be provided by the ionization from a particle. So for instance, if you take CF3I, which is class of Freon, put it in a situation where it's over here and it, as a superheated liquid, and let a muon go through it, and bang! As you can see, it nucleates. And this photograph is taken millisecond after that initial travel. You actually trigger by listening for those bubbles beginning to form, and you trigger your camera, and you can see this muon streaming through. Now, for instance, if you lower the temperature at which you're holding the heated liquid, so it requires more dense ionization to get that nucleation to occur. Muons are no longer, or indeed electron recoils are seen because they don't provide enough energy density in a small enough packet to allow a bubble to nucleate. Instead, the bubble, if it does try to form, just collapses because it doesn't get over threshold. But the very high DDX that you have associated with the nuclear recoil of either a fluorine or a carbon or what have you, or iodine from inside, the DDX is much higher for that, and in this case, they waited a long time to get this, but it's about 8 or 9 scattering sites of a neutron wandering through their target, which is of the order of 10 centimeters scale on this. It's wandering through the target, depositing enough energy at each of these sites to allow bubbles to nucleate. If you were to let the camera continue to run, let the detector continue to run, these bubbles would expand and completely blow your target all over the roof of this detector. So actually what they do is when they hear the bubble beginning to form, they recompress it to try to stop the target from, and this way they can take a relatively modest sort of minute scale amount of time to recompress the target, turn it into a superheated fluid again, and then look again. What they're of course ultimately looking for is the single bubble. Now this single bubble is actually just a single scatter of a neutron that got all the way in and out and only scattered once, but this is what a WIMP would look like in their detector. So there you have it, essentially a platonic ideal, and you can scale it up. This is 60 kilos, 60 liters, 40 or something kilos of target. 37 kilos of CF3I. And again, they have waited quite a long time for a neutron to scatter multiple times, and this is viewed in X and Y. So they can actually get the full position of this, and Z is pretty apparent, right? So they showed, for instance, that you can expose this thing to very high activity electron recoil sources, gamma sources, and it doesn't, at the level of in excess of 10 to the 10 interactions, you do not get a nucleation site because the DDX is not high enough. But if a neutron goes in, single scatter, multiple scatter, it nucleates. So you shield all the neutrons out, you don't give a damn about the electron recoil sources, and you just watch and you wait for it to nucleate. And this is what they did. Now, unfortunately, this experiment has been repeated a number of times, and while the technology is extremely promising, they have been tripped over by alpha particles. We didn't really talk about it, but alpha particles have a reasonably high DDX, so that they are also capable of nucleating. Now, usually the contamination is around the edge, so you can sort of see it in an XY that the alpha particles have nucleated near the edge, but they managed to reduce that level, but then it turned out there was some contaminants in the bulk of the thing, so the alphas were nucleating in the middle, but then they even got rid of that, and chemistry intervened at that point. Disaster in this sense. It turns out the CF3I can be a little bit unstable, because what they were seeing WIMPs in the last run that they've reported on, but they saw the WIMPs happening correlated by hours, and that's just not reasonable. They'd see nothing for a long period of time, and then over a period of hours they'd see apparently what were WIMP events. The fact that there's a time correlated, WIMPs are not expected to be in any way clumpy on that sort of time scale. So it was apparent that actually there's a bit of instability in the way that the CF3I propagates. So although we achieved, if you like, the platonic ideal there, the challenges of dark matter detection are such that right now we're still, unfortunately, really remaining at the R&D phase with that work, although we do wait for it to sort of really achieve some of the promise it wants. So we need additional information about interactions, I think, to convince the world, and indeed to do physics with, to do physics, we need ways of testing the signal. And of course, the classic way of testing any rare event particle physics experiment, which is turn the beam off, Doesn't work in this case because dark matter, being as penetrating as it is, there's no way you can ever turn its beam off. So you have to come up with ways in your detector to get as much information out of as simple a detector as possible, in order, I think, to get to the point where you can really convince yourself that you have something that's consistent with the dark matter signal. And of course, you're going to want to repeat it in a number of different experiments. So let's consider these gammas, these source of backgrounds, just for a moment. Does somebody here tell me? This is actually the governor of South Dakota, or the previous governor of South Dakota. He's now actually state senator, Mike Rounds, visiting the LUX site on the surface. But the question is, how many gammas per second does the governor emit? Or any of us, frankly. Does somebody hazard a guess what the gamma rays per second that individual might emit?
10 to 4.
Good guess. Yeah, somewhere between 10 to 4. 2,000, say. Lovely. I actually didn't appreciate this until we went on a site visit to WIP, the Waste Isolation Pilot Plant, and as part of the process to sort of put people's minds at rest in New Mexico, they set up this full-body gamma scanner, which are enormously expensive and not things you come across very often. And we were they made the mistake of leaving physicists in this room for an hour or two while they went off to do something. So we actually fired this thing up and climbed into it to see it. I actually had, until you see it literally appearing on this wonderful screen set that they had, I knew the numbers, but I'd never truly appreciated how active we are. So the point is, if I'm holding my dark matter detector, I'm setting it off 10 times a second with my gamma burden, right? And I just told you, kilogram per century, right? 1 event per kilogram per century. So the potassium-40 in this concrete, the conventional uranium-thorium burdens that so many materials, rock has, just not inconsistent with the sort of work we're trying to do. But the thing is, we have learned over the last, 20, 30 years, just how to do well. And this is, again, logarithmic scale, where I'm trying to give you a sense of what we're doing in terms of killing the gamma ray background. So the average, in the US, and this time I've chosen to use micrograys per hour, but if you want to think of it in terms of number of interactions in a kilogram per second or whatever, but in micrograys per hour, it's an order of 0.1, 0.3. Let's not talk about radon. Ramsar, for instance, it's about a 2 order of magnitude higher. Apparently, no additional medical, disease rates. Actually, frankly, better than they are in Ramsar. That's probably got more to do with their diet. But even controlling for diet and what have you, doesn't matter. Now, if we go to one extreme, in a reactor building in Chernobyl, about, 8 orders of magnitude, 9 orders of magnitude, above that, you didn't last, unfortunately. The poor buggers who went in, the firemen and the scientists who went in there, didn't make it out, or at least didn't live to tell the tale. Full body CT scan at the levels of 10 to the 4, 10 to the 5 on these units. Let's go the other way, though. So, for instance, a mile underground, it turns out we do have a lower rate by about a couple of orders of magnitude than on the surface, but that's not due to being underground, that's just the geology. The Black Hills are quite small mountains. Why? Because they're very old. They've been weathered down, whereas the Rockies up the road, right? Big mountains, young mountains, a lot more radioactive. So we have less uranium-thorium in the rock down there, but that's not why we go deep underground. We actually go underground because we're trying to escape cosmic rays. And I'll mention them just briefly here. If I hand my hand out here, cosmic ray muon's about 1 per second on the surface. You go a mile underground, it's about 3 million times less. So you're holding your hand out and waiting a few months for a single interaction. While that's not 1 per century, it turns out that by the time you've gotten down to 1 per every few months, your veto techniques are good enough to mean that you don't have any residual headaches associated with those guys. So going back to the gammas, what we're doing is actually we're really driving the gamma background by simply being inside water. You could, these days, and again, the neutrino industry, I think, had a lot to do with this, we know how to make water pure at sub-PPT levels of uranium-thorium. And if you think about that, that's really getting down to this sort of hundreds or thousands of atoms per mole level. It's really quite impressive. So this, for instance, we're using a 8 beta water tank, high purity, sub-PPT levels of contamination. And then the last thing is we have this a third of a tonne, which linear scale is about 50 centimeters. So you're in 50 centimeters of xenon. Xenon's actually a bloody good shield. So the detector is actively shielding itself, and for wonderfully subtle reasons that an awful lot of people missed for an awful lot of time, that shielding actually works not only for the shielding, if you like, that's in between the radioactivity on the outside and your interaction point, but actually all the volume behind shields you as well. Why? Because we're looking for dark matter. It's a single scatter. So if one of these gamma rays wants to try to come in and make a small energy deposition, and because it's a small energy deposition, that means it's a small angle Compton scatter. X-rays are no bloody good because they're absorbed in the first 10 millimeters or less of material. So it's got to be a high energy gamma, small angle scatter. It's got to make it out again. If it doesn't make it out again, it deposits too much energy, and it's clearly not a dark matter particle. So the quietest verified places on Earth are currently at low energies, are currently in the middle of these xenon detectors. And as you can see, that's got to be right, because if we're looking for interactions at 1 per century per kilogram, we have to have got there. So the other point to make, and I think I'm going to make this once, is that xenon doesn't have any natural radioisotopes apart from xenon-137, which is a double beta decay candidate, but that is a very rare process in its own right. So it turns out that this is the right kind of material to make a detector in which there's very little competing. So that's sort of, if you like, how we're achieving it. And for those of you that are used to looking at background spectra, this was an attempt to sort of bring a lot of them together, which is, conventional backgrounds, sort of right, let's see, 5 orders of magnitude up here. So this is just energy, logarithmic energy, background rate. Detector just sitting in the open here right now, up probably 10 to the 5, 10 to the 6. And then this is what we're achieving with various techniques. CDMS2 experiment I worked on, the sort of background. Do you remember I mentioned 10 to the 10 to the 0, 1 count per kV per kilogram per day? That's what we were doing was happening in Homestake. When Xenon 100 switched on, it was at this sort of background level. LUX, it's bigger, it's quieter. Down here, this is actually cosmogenic activation, these features here, these died away. Subsequently. Just to give you another sense of scale, this is pp solar neutrinos, so electron recoils from neutrinos causing electron recoils in your target. So when we go to the next phase, which is it's about 8 kilograms fiducial, around 6 tons, the dominant background is in fact just pp solar neutrino scattering electron recoils. Now you do have experiments like Borexino, say, or Snow, which went to look for solar neutrinos, and one of the questions one might ask oneself is, why aren't we using water to look for dark matter? Well, unfortunately, electron recoils firstly don't couple very efficiently to dark matter particles, but also these are non-relativistic collisions, so no Cherenkov light. So you then say, well, that's fine, Borexino, right? Borexino liquid scintillator, fantastic, except that carbon-14. You can't use hydrocarbon, organic scintillators because it's price prohibitive to remove the carbon-14 by isotopic separation. So that's why dark matter otherwise I think would have been sort of, you could have wrapped it up with liquid scintillators. That's why we've ended up with these targets like, well, latterly the xenon, say, because it is. And I do pop argon on here, and I think, in view of the time, it's going to be the only time I mention the argon, but argon, of course, is also a noble liquid, or a noble element, and can be used as a target, but it does have the natural radioactive 39 argon from cosmogenic production in the upper atmosphere, which I'm afraid gets into the argon. Now, you can go looking for argon in underground wells. It's been trapped there for a while. If you find an underground well that's a long way from uranium-thorium, which generating neutrons which transmute or interact with potassium, creating argon-39. If you can do that as well, you can get this down. So right now, the best state of the art is they have found argon underground with about 1/100th of the level of natural argon that you have in the atmospheric argon, and that puts you at a background level that's about where the Xenon 10 experiment was. For instance, it's about, this was a 10 kilogram detector. The challenge, what they would like to do, obviously, is get less argon-39. That's probably not going to happen, but at that point, argon does you enormous favor, which it turns out that it can reject electron recoils with a quite high level of discrimination. They hope, or it's been demonstrated at around the sort of 10 to the 5, 10 to the 6, I think it's now 10 to the 7, over 10 to the 7 level. The trouble is, you have your energy threshold slides right up. So actually what happens is the energy at which you can do this is very much higher energy, which is not so good for looking for dark matter. So the other thing I thought I would mention is just once, in one slide in passing, was just on this subject of directional dark matter. I had to mention this once. It is true that one of the absolutely definitive is probably the wrong word, but very convincing ways of observing dark matter is because the solar system is actually in motion around the Milky Way, that it means there is a sort of WIMP wind. If the WIMPs are assumed, and in some models they are, other models not so much, if they're not co-rotating, then in that idealized situation, our velocity at 260 kilometers a second towards Cygnus means that we get hit by a lot more WIMPs in the face if we're looking towards Cygnus than away. That will manifest itself very directly as a directional recoil, if you like. And if you can see the directional recoil, and this is an example, albeit at quite high energies, but what's known as head-tail, this is actually the head, and this is the tail. This is a CCD resolved image of allowing the ionization in gas to form this pixelated image. This one I think is taken from DMTPC. There are other experiments drift. So what you can imagine is locating yourself on the Earth, which is spinning diagonally, which can be used to effectively change the orientation of the WIMP wind relative to the detector, and you could imagine seeing these head-tail thing. The challenge is, can you do head-tail not at these energies, but at the much lower energies that again are associated with WIMPs? Also, this seemed a lot more tractable. In the typical pressures you're working at there, a cubic meter is of the order of about 40 grams equivalent target mass if you're being charitable. So the challenge is always going to be that can you get enough target mass? I mean, you'd what's the largest cathedral? Is it the Basilica these days? Yeah. Well, what do you mean these days? Has it always been? Anyway, I think that's right. It's basically I think it's St. Peter's Basilica. You'd have to, even to be competitive today with these gas detectors. Now, we're particle physicists. Hell, we've done crazier things than that. But it is true that with the current technology, and we don't even have the threshold, we still have a challenge. Albeit if we do discover dark matter, that will be obviously one of the experiments that we may have to call the Vatican about that one. So right. So LUX. Let me talk about LUX. LUX has gone. LUX is currently the sole member of Club Sub-Zepto. We're now at a sensitivity of below a zepto bar, and of course that doesn't mean very much. Let's get back to the units of 1 event per kilogram per century. Why? Because we have a fiducial total mass of about 1/3 of a ton. It turns out that we cut our internal region for sort of self-screening purposes, a little over about 120, 130 kilograms these days. And we're looking for events there. So the sensitivity is at this level of sort of about 10 per kilogram per century, and getting better. So I'm actually going to sort of pick up the speed. I want to show you a bit about the LUX detector. I told a group earlier I was going to show them this. I can't, because I do want to talk about it. So how does LUX work? LUX is quite simply just 1/3 of a ton of liquid xenon, gas on top. That turns out to be important. A set of grids to apply an electric field which is designed to drift electrons upwards. And we're watching the whole thing with 61 photomultiplier tubes top and bottom. If a particle comes in and interacts, the first thing that happens is that primary scintillation light is generated, and this is picked up at some kind of, and we are measuring at the single photon level. You can do it with photomultiplier tubes. You see single photons arriving, not with perfect efficiency. We measure about 1 out of 8 of the photons that are generated here actually generate photoelectrons spikes in the photomultiplier tubes. That's just simply a function of the sort of efficiency in the phototubes and our ability to capture all the photons. So this is this initial bump here from the light. We also generate electrons, and those electrons drift in that applied field. They don't generate light as they drift, but in liquid, but when they drift in gas, they undergo a different kind of scattering. They actually do inelastic scattering in the gas. It's kinematically not able to reach that inelastic threshold in the liquid at these sort of fields. In fact, you have to get very high fields to see the inelastic process there. So what happens is you get a lot of light being generated as the electrons leap out of the liquid into the gas. So you get a big burst of light, and of course it's very localized because it's a blob of electrons. The thing, so it's localized in time, it's localized in X and Y, you can clearly see the position. So this is what's known as a time projection chamber, and this distance here maps into the Z, and then the XY is just from the hot spot there. And the fantastic thing is we are doing this kind of trick, this TPC style, we are doing it with particle events that are down at below a keV, that are hundreds of eV level, because you generate a handful, but enough electrons and enough photons down at those low energies to actually be able to see something. So this is what the realization looks like. This is about 2 meters. That's a person sort of standing there. And this is inside a water chamber that's about 8 meters across. And we access all the cables and everything are running out of the top here. And this frame is just supporting the whole structure. But this is the detector here. Okay. So this is obviously a computer animation, but just to give you a sense of how it all goes together. This is, again, just this 2 meter chamber. We're just keeping it, this material is moderately radioactive, which is why we're just trying to keep some sort of distance between us and it. The components of the detector itself, this is, for instance, titanium. So that's very low we selected titanium with very low background, and then, of course, if you just look inside, you can just see that we have nothing really more than, so that's just a vacuum double wall to get the vacuum, and then this is just the 1/3 of a ton of xenon being watched by the 61 photomultiplier tubes, top and bottom. And every one of these materials, this is copper, for instance, very low background, titanium, low background. The photomultiplier tubes, we've worked quite hard to make them low background. So what happens if you expose the source? Well, one of the ways we've innovated in LUX is to be exposed by injecting tritium directly into the xenon. That, of course, would be a total disaster if you couldn't get it out, but it turns out we did prove to ourselves that we can, in fact, get the tritium back out of the xenon. In that case, it's fantastic, because what it does is it gives you, over from 0 to 18.6 keV, it gives you intrinsic electron energy decays, which are just perfect for calibrating the detector. And what you see is, this is primary light, which, if you like, maps onto energy of event, and then on this vertical scale is the ratio of the ionization to the photon, the scintillation signal. And it does have some energy dependence, as you can see, but we are able to, these days we're doing, this is 10 to the 3, we've got even more, 10 to the 4 events per bin. We're phenomenally high level of calibration and systematics cross-check. And then if you do something like take a americium beryllium or a californium source, and latterly we've actually just been using a DD neutron source and injecting that directly down a beam pipe into the xenon. These are nuclear recoils. Now, you may be able to see, but actually this red line here helps guide the eye. This red line is this red line here, this blue line here is this blue line here. You get a different ratio of this ionization to primary light signal for nuclear recoils versus electron recoils. And we use that in order to say whether what we're seeing is more characteristic of electron recoils, which case it's background, or whether we're seeing nuclear recoils. So the reality is, well, before we do reality, this is what a WIMP dark matter signal would have looked like in the LUX detector had the model that was being promoted by 4 other dark matter experiments, direct detection experiments, at the time we were running LUX in 2013. They had all seen signal in their detector, and the best sort of, or most likely case, this was taken from CDMS2, which was one of the experiments that was claiming potential discovery, that LUX, when we ran it for 3 days, 3 months, we would have been seeing about 1,500 events. And we did run it, and actually, at this rate, this was about 1 an hour, so we started looking, even Neil was going to pop in to see whether he could see these guys. We started running, and it was immediately apparent we were not seeing these guys enough. We'd run for a few days and a few weeks. It was clear that this favored model by other experiments was not, was actually turned out to be a systematic effect. What we did see is this. This is after running for 3 months. These are all the this is the electron recoil band. This is where we expected the nuclear recoil band, and we just basically see a sort of Gaussian-like distribution around the thing. Well, if you're really good at seeing, there is some slight suggestion of clumpiness here and actually here. You can't really see it here because the efficiency. We have cosmogenic activation. The xenon, when we ran this experiment, the xenon had, a couple of months earlier, had been on the surface. We put it underground, we run it for 3 months. There is a small amount of electron capture, cosmogenic activation still in there. I skipped too many slides, but it would show you why this feature here and this feature here are due to the cosmogenics. But as you can see, for instance, compared to this guy, there's just no sign of this dark matter signal. And of course, the way we analyze the data is with the traditional sort of maximum likelihood techniques, looking for whether there was any consistency with the dark matter model. And of course, what we ended up doing was placing just upper limits on the potential amount of dark matter that was in that signal. And because the LUX was so big, we were ruling out all of any of the models that other experiments have been favoring, and sort of moved the sensitivity further into the parameter space of.
There's a lot of multipliers in the water tank.
Those are just to pick up the Cherenkov light from muons that are traversing. Yes, well, as it turns out, at a mile depth with a water tank like this, you don't actually expect to get a signal from the muons that you're going to confuse with dark matter. But if you claim discovery of dark matter, the third thing somebody's going to ask is was it correlated with muons? so even though we're deep enough to not really need this, you put it in. When you run for 300 days as opposed to 90 days, you're beginning to get to the point where you do actually expect to see 1 or 2 neutron events correlated with muon traverses. So we may just be at the limit where we get luckier, if you like, and we get to see a neutron coming into the detector associated with one of these muons traversing. But as you get bigger, you get more and more sensitive. Then you do really need to get your muon veto sorted out. But it's really just the thing. So doing a bit of particle physics. This is the WIMP mass is uncertain. The cross section is uncertain. The LUX limit of sensitivity is this line shown here. And then what's been superimposed are a number of different particle physics models for WIMPs. So the history really over the last 25 years and where it's going to be is we've covered essentially about 4 or 5 orders of magnitude of models. Now, these models have, of course, evolved as our accelerator limits, have got better on new physics. We've also been moving everything down. But, the other way to put it is we having gone through, say, the early models were all up here. Your Dirac neutrino used to sit up here, cross-section around 10 to the minus 4 in these units would be around here. We've still got about another 4 orders of magnitude we can go until we hit essentially a sort of what, apart from ignoring directionality for a moment, is essentially an irreducible background. And that is the one that comes around from, one part of it is diffuse supernova background. The high energy GeV neutrinos that are ejected by supernova events from throughout the universe are just provide a background which will coherently scatter from the nuclei and will look essentially, as it turns out, very similar to a dark matter signal in terms of the recoil energy. The other thing which at slightly lower energies but is very dominant is the GeV neutrinos generated in the upper atmosphere that also will coherently scatter from nuclei and look a bit like, and will look fairly like dark matter. So this dotted line here, and this is from, for instance, coherent scattering of boron neutrinos from the sun, again at very low energies, it's a much higher flux, so it sort of kicks up like this. It's going to be difficult or more challenging to probe models which are actually underneath this region. There are ways of doing it, but it's going to take time. So that is a sort of challenge. So how we're meeting that challenge right now, and I should draw to a close at this point, is shown here, which is the same water tank here, 8-meter water tank, but we've popped inside it a 10 ton or 8 ton xenon, it says 7 there, it's about 8 by the time you seven inside here. So we're going from what is about 260 inside like this, we would be going to 7 tons inside here. So that's nearly 1.5 orders of magnitude, a bit more than, what's that, if you're 50. A scale up, and in dark matter sensitivity terms, it turns out that it's about 2 orders of magnitude in dark matter sensitivity. We are surrounding it by a liquid scintillator detector because we figure for the additional cost that does produce some significant additional leverage on eliminating conventional backgrounds because they multiply scatter. So we've demonstrated very clearly that I think as a cost trade-off, having a liquid scintillator veto or liquid scintillator detector around the xenon detector is a very effective way of managing any and controlling the risk associated with any additional background. So we're going to use this. This was recently approved by the Department of Energy and the National Science Foundation as what we call a Generation 2 dark matter experiment. Of course, we've been going for 27 years, so calling it Generation 2 is obviously a rather local notation. But nonetheless, will allow us to explore in terms of this WIMP mass versus cross-section. This is the LZ where we can go with the sort of 7-ton target. And it's not the only experiment. I was going to mention another couple of the ones, but I think in deference to the time, I'm going to have to be a little bit more circumspect there. So, yes. So I'm just going to, because I do love this experiment, even though I always say I'm never going to talk about it again. So let me just mention, I said I was going to talk. So Dharma Libra, why are they so sure they've seen dark matter? It's sodium iodide crystals being watched by conventional low background photomultiplier tubes, been operating since the first result in 89, they started operating back in 85, and then Libra thing. But why do they think they've seen dark matter? Because if you plot as a function of time, they see a modulation in their event rate. This is not all of their data, but it gives you a pretty good sense of how it's been going over the last 15 years. And this modulation would come about because the motion of the Earth relative to the Sun and the Sun's motion in the galactic plane, particularly this Earth velocity either adding to or subtracting from the motion towards Cygnus that we have will produce a slight modulation in event rate. So what they're saying is an annual modulation in the event rate in which they're seeing the detector at a level of 9.3 sigma, which is what it is now, so it's clearly well beyond statistical question. This is what they claim to be a detection of dark matter. Of course, it's an enormous and continues to be an enormous debate as to whether this is just due to, some uncontrolled systematic in their detector. And an example of what I sometimes refer to as threshold dinos. I think the community, I think we have a bit of a joke over this, as you can call them, threshold dinos. Why? Because as anybody who's been involved in experimental physics, you know that signals have a habit of appearing in your lowest bin simply because you can't control the systematics nearly so well. There, I think this is attributable, if you like, this lowermost bin dilemma. I think Rutherford used to talk about it, but certainly any experimentalist worth their salt understands this. It's also another example of what I sometimes refer to as if you like, Sisyphus' dilemma, or the Sisyphean index. I've worked on 5 different technologies over my time in dark matter, and it's been very clear that some of them have much higher Sisyphean indexes than others, meaning that if you don't literally sleep with the bloody things as I used to 24 hours a day, they would roll down the sodding hill on you when you went for a brief kip. You'd come in the next morning and find the damn things had changed. One of the things I think we've discovered with xenon is it really wants to work. One of the things I discovered with especially, say, superconducting niobium detectors is, boy, is that a labor of love to make this work. Fascinating systems, but if you want to do a dark matter experiment, I think you often need to, should we say, get away from being or working on technology that has a high Sisyphean index. The dark matter problem itself is sufficiently great that you have to do yourself many favors as you can. And we have seen, I think, in some systems with higher Sisyphean indexes, this tendency to make accidental and probably incorrect observations. So in summary, I mentioned this Generation 2 business. It's important just because I think it sets for the US mainly, but it really sets the sort of roadmap for discovery now. What's happened is that these experiments, while being relatively cheap, we put the whole of the LUX experiment went up for less than 10 million bucks. Usually when people ask, my colleagues have said, you know, especially in the HEP side, when they've tried to guess how much LUX cost, they've often guessed an order of magnitude more than that. We really did put up LUX for less than 10 million bucks. We're now entering a sort of era of these larger experiments, which are going to cost of the order of 30 to 50 million, say. It does mean there's a little bit of a dyspepsia, you know, taking place within the HP community. So unfortunately, they've had to limit the number of experiments they're getting through. It's the LZ, it's the super CDMS, and then I didn't talk about axions, but the axion dark matter experiment. That doesn't mean that other experiments won't get a chance to take place. It's just right now the priority, or the main funding is going to these experiments. And as I've shown you, it's going to allow us to really push sensitivity over the next 5 years larger. We have also seen tremendous progress in low mass WIMPs. There was a lot of interest in them because people started seeing signal. As it turned out, you know, LUX, we pretty much we did rule out all of those low mass signals, but that was because we improved sensitivity by nearly 2 orders of magnitude, you know, over the last sort of 2-3 years, by pushing really hard on low energies. And you know, we did learn about systematics, even if we didn't learn about particle physics, as it turns out. And then I should talk a little bit about, obviously at high masses, you know, the rate of progress is about, you know, 5 orders of magnitude over the last 25 years. I think it's fair to say that in the last, you know, couple of years, we've done over an order of magnitude. And one of the purposes of these xenon detectors, these noble liquid detectors, is really try to improve that sensitivity as rapidly as possible, so we can, given that we don't currently know what the scale of the physics is for the weakly interacting massive particles, it does improve our, you know, our chances of getting them before we're, you know, say. So, you know, spectrum discovery, always close. You know, maybe when I came into the field, it is fair to say we used to lure people in by saying it's 5 years away. I wouldn't even hazard a guess now. All I would say is that our ability to test the next 4 orders of magnitude is certainly well established now. And if, you know, with experiments like, and LZ is not the only one, but with experiments like LZ, we will be able to push through all of those additional domain in particle physics. Thank you so much.
So some people say that this WIMP miracle is gone now because
Yeah.
you have improved your sensitivity so much
Yeah.
that WIMP miracle is no longer with us and it can be axial. At least this is what my friends tell me. Can you comment on this one? And you are there for wasting your time. You should detect axions.
Yes, but on that, I mean, they're also saying that LHC is wasting its time then, are they? I mean, I think they're, you know, it's the Mark Twain thing, right? They're a little premature about announcing or calling one's death. I think it's still, obviously, it would have been damned elegant if the first time we'd switched on the Tevatron, the new generation of particle physics had come flooding out. It turns out that nature, you know, plays games at logarithmic scales, and, you know, our lifetimes, or those lifetimes of research, is not necessarily the same. It's very difficult to sort of, you clearly cannot write the whole thing off. All you can say is it's the very simple models that first got us into this one have already been ruled out. You know, if you get, you can argue that it's not as elegant as it once was, but shit, there's nothing elegant about our universe. I mean, honestly, you know, you would not have ordered this, you know, this dark energy, dark matter stuff. So as lovely as Occam's razor is, we all know that it's only selectively true. You know, maybe we do happen to have a rather ugly model of supersymmetry. Maybe it is one of these other theories. I mean, it's certainly the case that using direct detection, you can't completely exclude all dark WIMP models. There are plenty of other ways of going. Where it's going to get very exciting is if we have signal in one of the channels. You know, say it's indirect, but we don't have it in direct, and we're looking for it in the acceleration. We now know roughly where to look, or something like that. Then that is physics. You know, that's science taking place, because we're going to be getting thing. Obviously, the rate of improvement that we're able to achieve in direct detection means that we are quite excited about potentially discovering the WIMPs first in the direct detection. Certainly in terms of, you know, dollar or sensitivity per unit time and per dollar, it's impressively rapid. The number of dark matter, a number of particle physics models that we're sweeping through. But it is, you know, yes, it may well be the case that when we look back, I mean, I think it was Douglas Adams came up with this wonderful idea of, jokingly, that a book falls through a wormhole, you know, on your particular research field, you know, and say it came from sort of 50 years or 100 years hence, and you rapidly open the thing up to the chapter on dark matter, you know, and you read it wanting to know what the answer is, and you find just written as a footnote at the bottom of the chapter, sorry, not on the composition of the universe, you say it was popular at the turn of the century to believe that we were surrounded by this all-evading ether of dark matter particles. And I use the term ether intentionally, ether of dark matter particles. Of course this turned out to be total rot, you know. We could be the thing, I mean, you know, yeah.
Many years ago there were some experiments done in the genetic fridges, direct calorimetric experiments. Whatever happened to these things?
I used to be one of them. I used to spend a lot of time at 20 millikelvin, you know, intellectually. And of course, one of the challenging things about that type of detector is you can't get in and just fiddle with it. You know, you've got to cool everything down, and if you don't get your engineering right, you then got to wait days or weeks, depending on how big it is, to warm it up again and what have you. It was the reason, and my niobium detector used to run at 50 millikelvin, 60 millikelvin. We used to, when we were designing detectors like that, we really were convinced that the WIMP masses were probably pretty low. But of course, as accelerators swept in and the mass scales went up, you know, we tended to think less about low mass WIMPs and more about higher mass WIMPs, and then it seemed more reasonable to be initiating experiments where target mass was the thing you could achieve. And that creating these calorimeters, which were often, you know, required quite bespoke techniques. I mean, I spent a year and a half in the clean rooms at Stanford making, you know, CDMS, thin film superconducting zip detectors, as we call them, you know, and trying to get the formula right. And as anyway, you know, what's the other one? Oh yeah, we were making it on germanium, not silicon, you see, because it's better for dark matter. But if there's a reason why our semiconductor industry is based on silicon and not germanium. And it's not because of the semiconductor properties of silicon germanium, it's because of the bloody oxide, right? Silicon oxide is a fantastic insulator, germanium oxide blows. But we were trying to make superconducting thin film circuits on the top of germanium. And if the water gets in, you know, everything peels off. And you know, it's wonderfully elegant stuff, but you really have to reinvent process technology to be able to make those guys. And then somebody just wanders in and you write a proposal and you say, oh, by the way, we need 500 of those by Christmas. You know, because they weigh half a kilo each and we want to do 250 kilogram target. Compared to that, xenon, somebody wanders in and says, chaps, we need a, you know, 350 kilogram target. It was like, just give us a bucket. And you poured it in, and the neutrino industry had done the same. So the reason, the relevance of those cryogenic detectors, as we sort of call them, is something. It's certainly true that you can get very low energy thresholds, although I'll show you, I didn't in this talk, but I can show you results where we've seen very low energy events even in these noble liquids. But people sort of argue that maybe using milli-electron volt excitons is a better thing to be using than EV scale excitons if you really want to talk about particle events down at the you know, sub keV recoil levels, which you know, if you have GeV or sub GeV WIMPs, is sort of where you're going to have to go. So the way CDMS have sort of managed to, I mean, what's amazing is CDMS discover WIMPs, right? They get funded, they then rule those WIMPs out, and they still end up in a situation where you know, super CDMS, I love them dearly, but I do find the logic wonderfully self-referential, is they discover WIMPs here, they all get ruled out, but they still basically end up giving people a lot of excitement over this parameter space here. So that's what we're doing now. We are using, or they will be using now under super CDMS, there'll be tens of kilograms because you're up at higher cross sections, so you don't need tons, you can do it with tens of kilograms. You go look in this region down here, and then, you know, we can debate. I mean, when I started, this was the region we thought we were going to be looking for dark matter, and then, as I say, the accelerators pushed the mass scale of the physics up. But then, you know, you go back and you say, well, look, accelerators only rule out certain classes of models in terms of, you know, this high energy mass. You can have classes of models, you know, this so-called asymmetric dark matter, for instance, or what have you, which do indeed give you events which are down here. And actually, you know, I'm sorry, I'm being naughty. I shouldn't think, you know, it's reasonable. It is, you know, it's kind of reasonable to go look for them. If you're in a position, if you've got the technology, why don't you do it? Although I do worry a little bit that this area has been fabricated a tiny bit based on a signal that never was. But we'll see. Anyway, this is the parameter space that Super CDMS, which is now going to be built at Snow Lab, is going to explore. And as you can see, it really is few GeV down to tenth of a GeV level, which does require cryogenic experiments, I think, for the most part. I mean, I think I could build a specialist noble liquid-based experiment, but it would require, for instance, we really have to get on we really have to improve our photodetectors, get them out of this sort of 30% quantum efficiency level, get them up to 100% QE. And because we need much smaller targets, we could improve the light collection. We could do it with ionization only. We've got some lovely ideas about ionization. As I say, I can show you plots of detecting 140 EV less than in ionization, actually well with, fully resolved in a 3-ton detector, sorry, in a third of a ton detector. Anyway, sorry, I should, yeah.
Well, I was just going to suggest that we, on the subject of cryogenic detectors, move out of this nil-Kelvin environment.